Welcome back. We will be discussing now today a different type of flight regime. So far, if I recall, we were having an assumptions. Of course, we are assuming the airplane to be a point mass. We are not bothered about the moment of inertia of the airplane because we are not discussing anything about the rotational property of the airplane. We are talking about cruise, talking about climb, descent in a rectilinear motion, right? We also had an assumption they are unaccelerated, that is, the forces are balanced. Okay. Of course, there was an implicit assumption that moments are also balanced. That is, I am not bothered about this. I am saying the airplane is going like this. No such rotations are happening because moments are implicitly balanced. In the second course, you will know how the moments are balanced. That's a different matter altogether. But assumptions are this. Right. Now we are going to relax one of this condition, and that is we still believe that we will be following point mass. However, this time we will say it is accelerated flight. This assumption that rectilinear motion unaccelerated, that is relaxed. So we will be terming this session under the title accelerated flight. You know, whenever we think of an airplane, the young man will always think, oh, airplane, I should do this, I should be able to do this, turn, I should do roll like this. Like when you buy a motorcycle, you never think of only going duck, 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 duck like this. You think of, I should be able to take a sharp turn, I should be able to accelerate very fast, and that is what is the signature of a youth. And in aerospace, the adventure will always remain as long as aerospace remains growing. Okay, so this part of youth, part of that adventure is an integral requirement to be a good aerospace engineer. So now we will be talking about accelerated flight. Okay. Let us first discuss about pull-up. What is typically a pull-up? Assuming I am going like this, say for your clarity, I am going like this, lift equal to weight, thrust equal to drag, and I suddenly increase the lift. So what will happen? If I increase the lift, that is, lift is more than the weight, what will happen? See, please recall, we have agreed that lift is perpendicular to velocity. That is how we have defined lift. Okay? So now from here you think, if a body is moving in this direction and you are pulling it by a string, it's a tension, what happens? It goes into a curved path, right? And this force is perpendicular to velocity. This reminds you about centripetal acceleration. Am I correct? So we will be using that understanding to model a pull-up maneuver. So let me draw. This is the airplane, this is the lift, this is the weight. If you want it to go for a curved path, and since it is going in a curved path, so it is no more unaccelerated flight, it is an accelerated flight. Okay? So if I draw this diagram like this, and then I try to write equation of motion, again assuming this is a point mass, so we have not relaxed this, and of course we are assuming the moments are balanced. Okay? So then I can write, see, lift, which is now not equal to weight, right? If it is going like this. So I write lift equal to NW, where N is the load factor, which is nothing but ratio of lift to weight. So now lift is not equal to weight, lift equal to NW. So this is NW. So if I now write the equation, what will happen? NW minus W will be equal to mv square upon r, where r is the radius of turn. It's in a vertical plane, okay, like this pull-up. So what? How do I understand from my class 11, 12 understanding? This is the net force perpendicular to the velocity vector. More importantly, NW is perpendicular to velocity vector. And if I see this diagram, see this force which is responsible for giving the centripetal acceleration. Okay? And now if I do little manipulation, I can write n minus 1 W is equal to m v square upon r, or I can write r equal to v square by g n minus 1. This is the radius. And if I want to know what is the angular rate, omega, you know omega r equal to v or omega equal to v by r. If I use the relationship, then I can write omega is equal to g by v n minus 1. Let me check. R equal to v square by g n minus 1 and omega equal to g by v n minus 1. What is the message you are getting out of this? Yes. Let us come back here. If you want R to be minimum, I want to turn like this, R minimum. How can I achieve R minimum? R you can achieve minimum if for a given V and given value of G, if N is maximum. What is the meaning of N is maximum? That is, you have a high load factor. How do you get a high load factor? You should have a very effective wing loading, very effective lift distribution on the wing. So all these things will get coupled when I think in terms of R minimum. R minimum is N maximum. Right? Similarly, you could see for a larger angular rate, again for a given V, N has to be large, which is, by physics, it is fantastic, because unless you have the lift, who will do the pull-up? It's the lift only. Same time, you could see that R is also dependent on V, omega is also inversely dependent on V. This is also an observation you must have. There is another maneuver called pull-down maneuver. Where I can, it's like inverted flight, okay? Here the lift acts downward and also the weight is acting and it is going in a circle in a vertical plane. If I now write same equation, I write L plus W will be responsible for giving centripetal acceleration, and I know L equal to NW. So by manipulating these two equations, I can write R equal to V square by G n plus 1 and omega is equal to V by R, that is equal to G n plus 1 by V. Correct? Here also you could see if I want R maximum, R minimum, then N has to be maximum for a given speed. If I want omega to be very high, N has to be maximum. Naturally, this is true because if I want a very sharp turn, this is a lift that is going to do all these things. And lift is more, then the load factor is more. Okay? So it is consistent with our understanding how that whole mechanics is going about. Once I cover this pull-down maneuver, now automatically it comes to our mind why we are restricting to vertical plane. Rigorously used maneuver, or the maneuver is the turning flight, right? You turn like this. Now think of, if this is the airplane is flying like this and it wants to turn in a horizontal circle. That means I need to have a force which should be towards the center of the circle. So where from I get this force? If the wing is like this, I don't get, because lift is like this. But if I bang this airplane, then the lift is now inclined. And one of the component, horizontal component, this will be responsible for giving me a circle in the horizontal plane. I repeat, if I am flying like this is the lift. If I want to take a circular turn in a horizontal plane, I need a force in this direction. So what I do, I bang the airplane. The moment I bang, this horizontal component will be responsible to give a force in this direction, and because of that I will be taking a circular turn, or we say turning flight. Okay? If this is understood, the modeling becomes simple. Let me draw it. See, we have banged the airplane by angle phi, This is the lift, this is the weight, this is again phi, and this is, I call it Fr, that horizontal force which will be responsible for giving me a motion in the horizontal plane, a circular motion in the horizontal plane, a curved motion in the circular plane. So now from this force diagram I can write L cos phi equal to W and Fr equal to under root of L square minus W square. From this triangle, you see, this is the lift, this is the Fr, this is the weight. So I can resolve the weight, one along this, so I can write this simple. Okay? Once I write that, now again I know lift equal to NW. It's the load factor. Right? So I can write Fr as under root NW square minus W square. So after doing some manipulation, I can write W under root N square minus 1 is equal to M V square upon R, because this Fr is only giving me the centripetal acceleration. So I will write this Fr equal to mv square upon r. What is this r? R is the radius of turn in the horizontal plane. That is, if I am turning like this, so what is the radius of turn? That is r. And what is this Fr? Fr is the horizontal component which gives me enough force so that I have requisite centripetal acceleration to ensure a horizontal turn. Now, if I write this, mv square upon r, for m, for your completion I am writing m is w by g into v square upon r. And now if I do little bit of adjustment, I can find out an expression for r as v square by g under root n square minus 1 and omega as g under root n square minus 1 by v. So again you see that if I want radius to be small or minimum for a turning flight, I need n to be large, which is fair enough, because after all n is nothing but lift divided by weight. N large means lift is more than the weight and lift is doing all this activity. So we are happy about it. Do not forget here, some component of weight is also coming in this case. The Fr, if you see, is L square minus W square. So let us summarize and try to get a generic feeling about this turning flight. We have seen R for pull-up as g v square by g n minus 1 We have seen R for turning flight as V square by G under root n square minus 1, R for pull down V square by G n plus 1. Now think of a situation. Let's say n is large. When you talk about accelerated flight, our aim is always to go higher n. Right? Otherwise, why do you want accelerated flight? A natural tendency, I should fly at a higher load factor. Okay. Suppose n is large, and we do an approximation, n plus 1 approximately equal to n minus 1 equal to n. Okay? Or I can, to be more precise, I can write n square minus 1. So this is an approximation that n is large. Okay? For example, if n is 6, then it is 1 is neglected compared to 6. Okay? Just to get an idea about some very important understanding for a designer, because all these things are from the mechanics. But the designer should translate this to its configuration of an airplane, which should be capable of generating requisite forces to achieve all these parameters, right? Performance parameters. So if I apply this approximation here, I get R pull up is equal to V square by Gn. Again, R turn also I get as V square by Gn, and R pull down also I get as V square by Gn. So we have seen that if n is large, then I can express R as V square by Gn, whether it is a pull up, pull down, or a turning flight. Okay. Similarly, you can show omega equal to Gn by V. Now we want to extract some information for a designer. That is, the important question is, if I want to make an aircraft which is capable of generating radius of turn, let's say A1, some value, then I must ensure that the design layout is such. And design layout of what? Design layout of primarily wing, because wing is giving this force. So how do I connect one of the wing important properties like wing loading with this R or W, angular rate? That is our aim. And keep this in mind, R equal to V square by Gn if n is large. What we are doing? First we are writing L in nothing but half rho V square SCL. From there I am getting the expression of V square. V square will be 2L by rho SCL. No issues. Now since R equal to V square by Gn, I substitute V square by this expression. So what I will get? For V square I will get 2L rho SCL, and Gn is here, G into n, where n is the load factor. What is n? It is a load factor, so n equal to L by W. So I will be replacing n by L by W in the next expression. You see, 2L rho SCL 1 by G. Instead of n, I am writing L by W. After that, I realize this L gets cancelled and W comes on the numerator. So I can simplify this expression as 2 by rho W by S 1 by CL into G. Or the final expression comes radius as 2 by rho 1 by CL to G by W by S. As I was telling you, after all, this force is coming because of wing, and all the important property of the wing in relation to lifting characteristics is wing loading. Because if wing loading is small, that means it has a large area, wing area. So now see here, our aim is to get R minimum. And what does it say? If for R minimum, I must also ensure W by S minimum, keeping other thing constant. Or it also tells that if I want a particular R, what should be W by S? If I want a particular R, what should be W by S? Or if you want a particular angular rate, what will be W by S? Please also realize here, if I want larger angular rate, very fast turning, again it says the wing loading should be very, very low. That means larger wing area means more lift and very consistent. So it's a simple manipulation, rearrangement of whatever we have learned, and with some realistic approximation, how wonderful results we get, which are so useful for a designer. Clear? That is the purpose of this course. That whatever performance we are talking about, finally we'll ask a question, am I in a position to give the designer the right insight in terms of laying out his component? So here at least one thing we have done and understood for ourselves, that if I want a particular radius or particular omega, what should be my wing loading? Please understand, when you select the wing loading, it may be selected because of many other criteria, because of range, because of cruise mission, because of climb mission. There are so many requirements will come. But as a good designer, we need to know for every mission what is the wing loading required, and finally you take out, freeze a wing loading which try to satisfy most of them or satisfy most of the parameters, most of the mission requirement in a weighted manner. Like if you are designing a transport airplane, then you give more weightage for wing loading for cruise performance. Right? Like that you have to be smart enough to get an optimal configuration. Thank you.